Today we celebrate the first glorious anniversary of the information purification directives. We have created, for the first time in all history, a garden of pure ideology, where each worker may bloom, secure from the pests of a contradictory thoughts. Our unification of thoughts is more powerful a weapon than any fleet or army on earth. We are one people, with one will, one resolve, one cause. Our enemies shall talk themselves to death, and we will bury them with their own confusion. We shall prevail.
On January 24th, Apple Computer will introduce Macintosh. And you'll see why 1984 won't be like 1984.
So that commercial aired once in 1984 during the Super Bowl, and this was 25 years ago now, and it was when Apple first debuted the Macintosh. And at the time, they were facing Big Blue, IBM, and those IBM PCs that most of you probably haven't even used in their original form, but it was a big deal as to what the Apple had begun to do in 1984 with the industry and with computers as we now know it. And today is focused on precisely that general world of hardware. We spent much of the semester working our way on up. We went through C, we went through PHP, a little JavaScript, and Ajax, and XHTML, and all of that. And then today, finally, we'll come full circle and actually look underneath the hood as to how all of this magic has been happening. When you compile something with GCC, when you run something with PHP, what is in fact happening underneath the hood. But a few announcements first. So one little copy-paste fail. This handout is indeed about quiz 1, not about quiz 0, which the first sentence says. My apologies. But yes, quiz 1 is in on Wednesday, 11/18, and do peruse the handout here for all of the available resources coming up at you, including review sessions and quiz review in sections. Also, take note that on Monday, we're going to be having a few guest lectures from the computer science faculty. Each will talk a little bit about computer science beyond CS50 and specifically some of the courses you can take. It's actually much more exciting taking computer science courses here these days than in my day, where pretty much after you took 50, you took 51, and after 51, you took 121, and after 121, you took 124. Like, there was a very clearly defined path, but there wasn't much digression from it. Now, there's so many more faculty and courses that after CS50, you guys will be able to take, if you so choose, for reasons of majoring, minoring, or just for fun, CS51, which is about functional programming and abstraction, which you'll hear a little more about on Monday. CS61, which is about systems programming. It's in that course where you defuse the binary bomb, that piece that I described a while back. You can take 121 next fall, which is a theory course and speaks to the fundamentals of what computers can and can't do. CS124, which is data structures and algorithms, which picks up essentially where we left off with hash tables, trees, and tries. CS171, which is about visualization and taking interesting large data sets and presenting it to humans in ways they can understand. CS105, privacy and security, which is more of a seminar course where you talk about the implications of various technologies on society and its privacy and security. CS179, which is a new course in which you'll actually do iPhone development and focus on the design of good user interfaces. So there's quite the platter of courses from which you'll be able to choose this spring, this coming fall. And realize, too, at the end of this course, CS50 is a terminal course for many students. Usually about half of the students in 50 don't take computer science again, and that's perfectly fine because the course is meant to provide you with enough background, enough skill set to actually go off and do interesting things even beyond the course. But realize that if you are interested in minoring in computer science, the department is quite eager to entice all the more students into it, and you have many different things to choose from these days. Majoring, all the better, but even if you just want to dabble in computer science, realize that this course in particular opens a lot of doors within the engineering school, so do keep that in mind. We'll have a little cheat sheet probably on the website or on paper on Monday just to give you a more clear sense than this verbal tour as to what awaits you. So one pitch before I turn things over to a couple of other folks. The first is this one here. So the website is now up as promised. We do indeed want some TFs and CAs and graders. What does this mean? A teaching fellow for this course, as you may have inferred from the person you've been working with all term, is someone who leads sections, who grades problem sets, who works with students one-on-one in office hours, fields questions on the bulletin boards, and does all those things you're familiar with TFing. I would say that TFing 50 is a fairly unique experience. It's definitely intense, perhaps as intense as taking the course, but so much fun, and dare say so much more fun being on this side of things than on that side of things. And it's a nice way to maintain, to remain part of the community that you might feel. CAs are volunteers, CS50 alumni who offer 2 hours of office hours per week. It's largely self-scheduled. It's meant to be very flexible so that we can keep as many alumni involved in the course and to help their successors in the course in the computer lab. And then finally, graders spend a few hours a week helping out with key sets. And finally, that's enough from me for the moment. Let me invite an alumnus from CS50 and a former TF and sysadmin and now president of HCS, Keito Uchiyama. Oh, sure. Yeah. Let me get him a microphone, which is over here. OK. All yours.
Hey, my name is Keito. I'm president of Harvard Computer Society. Today I'm here to invite you to an event that we're holding on Friday in conjunction with the Cs and CS department faculty. We're holding CS concentration cider and pie. So this is your opportunity to eat cider and pie. Well, in fact, it's actually for people interested in CS, people already concentrating in CS, people thinking of secondary fielding in CS. You know, if you want to take any of those courses that David just mentioned, it's your opportunity to meet CS professors and also upperclassmen who are already concentrating in CS. So it's a great opportunity to ask questions. And it's not just a CS professor kind of thing, because now you can ask people whether that class is, is 124 actually a good class? Professors won't tell you the real answer, but upperclassmen will. So as it says here, it's a great opportunity to meet faculty, learn about cool classes. You can meet CS undergrads, eat the food, win great prizes. We're still deciding that, but we are sure that there will be great prizes that you can win. And also, it's it's one in a kind. We've never had an opportunity like this, at least in the 3 years that I've been here. So it should be great fun. So that's CS concentration cider and pie. We ask that you RSVP on our Facebook event. If you want to RSVP at CS, go to hcs.harvard.edu/cider. That's harvardcomputersociety.harvard.edu/cider. You don't need to RSVP, so you can just show up. It's Friday, 3 to 4:30 in Maxwell Dworkin lobby. And if you don't know where Maxwell Dworkin is, you can use David's awesome maps.cs50.net tool to look it up on the map. So thank you, and have a great time.
Thanks very much. Put this back to Jensen. All right, so one pitch. If you didn't pick up your Shuttle Boy card, we have some with the teaching fellows on your way out today. It was kind of funny. We were looking over, so we have this form on the course's website now, as some of you may have noticed, and we wrote a little script in PHP that inserts registrations for Shuttle Boy cards into our database. And what was funny was to see all of the interest in this card on like Thursday and Friday after Wednesday's lecture, when we actually handed them out in person. So this little request form became this veritable list of who was not here on Wednesday. The irony is they're probably still not here today, but that's okay. We send them our best, and we actually got some 400 plus responses, so we'll start mailing those out to your friends who probably filled out that form this week. A big shout out to our own Drew Robb, who has completely trounced everyone on the big board. I looked up the word for this. It's 113 quintillion dollars that he has now made atop the big board, really putting to shame the leaders from last week. So this was all just for fun. Clearly, there were some opportunities to take advantage of here, but congrats to Drew and all of you nonetheless. So without further ado, coming at you now, last advertisement today is store.cs50.net. The CS department actually has a tradition of having silly little t-shirts and whatnot at the end of the semester. I still remember my I Survived CS51 t-shirt from many years ago, and so we've continued on in that tradition. And thanks to this fancy website, can we sell all sorts of things to ourselves and such. So feel free to take that out, but allow me to indulge us in a little display, perhaps, of what's been designed by our own TFs this year.
I'm too sexy for my love, too sexy for my love, love's going to leave.
Well, what do we have here? Marta, our great walkthrough star, who does not only know how to lead perfect walkthroughs, but also has a great sense of fashion, wearing a black t-shirt with 9 problem sets on it. And then we have Alex Hugon, our very king of the office hours, the Super CA. In a recent interview, he said that with all the 9 problem sets designed so close to his heart, he can program better and he can help more students. And then we have here Rose, our Super TF. She is wearing a property of CS50 sweatshirt, which she said is a great addition to any Halloween costume. Well, cat. Well, this is CS50.
Okay. So as you know, final projects are coming up, as is the CS50 Fair, and we CS50 were particularly proud to see very recently that some of our own CS50 alumni turned teaching fellows, some of them now, have been awarded a wonderful prize from AT&T. Some of you may have seen this float around the house list. Some of you may have on your own iPhones and iPods the Rover app by Harvard student agencies, and this actually grew out of a CS50 final project a couple of years ago, and I thought I would give them a moment, give them a little bit of a CS50 shout out here by showing you this few-minute video that they put together with AT&T. So if you can think of something as magical yourselves to do this year, perhaps it will be your video we show at next year's class. Here we go.
Hi, my name is Winston. I'm from Virginia, and I study physics here at Harvard, but I just really like working with my hands and making things.
I'm Joy. I'm from San Diego, but I'm Canadian, majoring in computer science and minoring in visual environmental studies, and I like good design and intuitive user interfaces.
I'm Cameron, and I'm from Colorado, and I'm a computer science concentrator here.
Okay, my name is Drew, and I'm from Hawaii, and I study physics, math, and I enjoy programming.
My name is Alex. I'm an engineering major from New Jersey, and for a very long time I've been interested in making mobile devices more useful to people.
Rover is a mobile platform to connect students with the community. So in the first version, we implemented a student-written guidebook into a mobile format that had listings as well as a deals platform for merchants to instantly connect to the students.
We also hope to connect students to their peers through student-to-student interactions. For example, student groups are often interested in getting more students to come to their events, so instead of posting flyers on a bulletin board, we can post flyers on Rover. Also, for example, you can have a free food feed, somewhat similar to the deals feed, where anytime there's an event on campus that has free food, students can take advantage of that.
And this platform is also a lot of potential for administration to communicate with students in a timely fashion. Almost everyone has a mobile device, and so this platform would be a quick way to reach out to students. Also for students to professor communication could be simplified a great deal.
All of this we hope to do with social networks. So for example, if a student who's a friend of yours is taking advantage of one of the free food deals, or is visiting a local merchant that they like, or has had a great experience with a professor, we want to broadcast that to all of their other friends who are also using Rover.
And lastly, at the back end of all this is analytics for our partners and merchants so that we can know exactly who's clicking on what and when. And this really provides business intelligence and usage statistics for us so we know what's most useful for students.
Rover is unique because it's an application that's written for students, entirely by students, with students in mind. All of the content on Rover is produced by students. All of the deals are things that students really want. What student doesn't want a free burrito, for example? We read about the winners last year, and we found out about how AT&T Big Mobile on campus helped them expand from just one campus to a number of campuses nationwide. And so by entering Big Mobile on campus, it really helped us think about how can we take what we've done here in the Harvard Square community and expand it nationwide.
Winning this contest is just a fantastic experience to work with AT&T people to really bring out, to expose our applications to perhaps a larger audience than we ever could have even pitched it to without AT&T. So it's just a tremendous opportunity for us. And the fact that we have some nice prizes too doesn't hurt as well.
And there's hundreds of applications being developed every day, and it's sort of sometimes hard to distinguish yourself from all the other great applications that are being developed. So this is a huge help.
And I really like making things that our friends are able to use. I like making things that I like to use, and I know the application that we made with Rover is something that I consult 4 or 5 times a day.
Just to connect students and like local businesses would like to get students in here, local theaters, local arts, and it's just the community, and we think that that connection can be really powerful.
So right there, if you have an iPhone or an iPod Touch, and congrats to our alumni and where they've taken that. It's worth noting, lest you be quite awestruck by what these guys have all pulled off, that there's kind of this unspoken rule in programming where anything you might ever want to do, and you've probably experienced this, probably takes twice as long, 3 times as long as you actually expect it to. So realize that this product is actually the work now of a couple of years of ongoing development. So realize that don't worry that the bar has been set so high for your own final projects. What these guys essentially did for their first version was a very functional and very nice prototype, sort of version 1 of this all, and then they've continued to build on that as well. So we hope you too will dive into something that interests you, if not for just the duration of the semester, even beyond. So congrats to those guys. All right, so today's goal is to focus a bit on what's been going on underneath the hood. So what do we mean by that? Well, we took for granted for some time that you can write programming code in a language called C. You can then run a compiler called GCC, and out of that comes a program. And just in English, what does it mean to compile a program from source code into object code? Anyone at all? Yeah, back. Okay, so take text and interpret it, or let me tweak your words, convert it to binary. So take something that's sort of pseudo-English, pseudo-code, or actual code. I'll run it through this program called the compiler. And the output of that is not just ASCII characters that humans can read, but it's zeros and ones that actual CPUs understand. So what does it mean when Intel says Intel is inside, or you see this little sticker on PCs? Well, that means that the CPU inside of the computer was made by this company called Intel. Now, what does that mean? That means that they decided some years ago now, that every CPU, the brains of a computer, would understand certain instructions. And what's rather mind-blowing is that the instructions that all of our programs, whether PSET 1 or PSET 8 reduced to, are basic things like addition and subtraction and multiplication, moving something from memory from here to here, loading something from disk from here to here. These very basic primitives that we completely take for granted now are really what compose all of the programs you guys have been writing. So just to put this into some perspective, let me go over to a terminal window here, and I'm going to open just a file called hello.c. I didn't bother printing this out because it's pretty familiar by now, and that's all there is to this. This is our canonical Hello World program. Well, this language C was actually an enhancement some years ago over a language called assembly language. So what you're about to see is a language that's much closer to the hardware. It's much more arcane, and it's certainly not nearly as much fun, if I'm even allowed to use that word in this context, than programming in C. So what I'm going to do is run the compiler, GCC, but I'm going to use perhaps an unfamiliar flag. I'm going to say -S, and then I'm going to say hello.c. And what I'm going to get as output per ls here is a hello.s. So this is an intermediate file that we actually never really see, not by default, but inside of here is what the compiler is doing for this very basic program. So this is an intermediate step between C source code and what's called object code, zeros and ones. Well, what do I mean by that? Well, let's see. There's really not much to this file. It might look a little cryptic. Let me shrink down the font a little bit and reopen it. There's really not much to it. 20, 30 lines here, and there's some new syntax here, and all of this is actually specific to Intel inside. Because I'm running this program on a computer that has Intel hardware inside of it, these are literally the instructions that that CPU understands. Well, let's see if we can't make sense of some of this. So at the top here, this seems to be somewhat uninteresting. Apparently the original name of the file. Here's a .section directive, whatever that means. .ro. What might this mean? .ro. So read-only. So read-only data apparently comes here at the top. Now, why does that make sense? Well, just below this read-only data section, there's this cryptic string, but then something a little more familiar, namely the string hello world, which I hard-coded into my program and is therefore itself a read-only string. I could change what, I could add strings to this program and such, but this is the one I hard-coded in here. So there we have this piece of data. .text, what did this denote? If you can think back a few weeks, what is the text section of your program? Anyone recall? Say a little louder. So what you were coding, so this was the actual program, the code that you actually wrote. There were a few sections. Remember this rectangle? We had the heap, we had the stack, we had initialized data, uninitialized data, and those last two related to global variables. But then above everything in that picture was the text section, and text just meant your program. So this actually makes sense because below text here comes our program. So this looks like here comes a function. It's apparently called main. All right, here is the main function. What goes on here? Well, these are these very basic primitives that I alluded to earlier, and some of them we can infer. Looks like there's a subtract operation, an AND operation, a move operation to move things around in memory. Add is in here as well, and L usually denotes long, so these are actually manipulating 32-bit values in this case here. But that's it. That's all it takes to implement Hello World. And some years ago, if you wanted to write Hello World, this was the stuff that you wrote. Rewind a little further, and what you actually wrote were punch cards, right? Things with holes and whatnot that you actually fed physically into a machine, and it would parse it. So we've come a long way. And certainly if you think now to implementing something in PHP, like you did this past week and will this next week, we've come a significantly far way here. But it's all the same stuff that's been around for 20, 30 years, even since Apple debuted that particular video. So what's really going on? Well, let's take a look at let's come back to this picture in a moment and consider this. So when you compile something, we've kind of been waving our hands or taking for granted some of the things that go on. None of them are very complicated, but they all seem to happen at once. So when you run GCC, there's 5 steps that happen between the time you write your code and run your code. So the first step is called preprocessing. So preprocessing, we've actually used ourselves. Anytime you used /include or /define, if you saw that in certain pieces of code we gave you, that's actually preprocessor directives. And GCC first does a pass from top to bottom, left to right over all of your code, and anywhere it sees sorry, I think I might have said slash, sharp symbol, the sharp symbol, and then include or sharp define, it says, oh, this is a preprocessor directive. Let me do something with this. If it's sharp define, what do I want to do? I want to do a find and replace for all of these global constants and replace it with the actual value that's been defined. If it says sharp include, I want to go grab the foo.h file, open it, and literally paste its contents into this location in the file, and then proceed with step 2. It's step 2 when your code is actually compiled. So we've kind of clumped all of these steps into just this one big word compiled, but compiling is really the second step. You've now got a big piece of code. All of the sharp includes and sharp defines have actually been pre-processed. So now the compiler, GCC, takes all of that code and converts it from your source code into assembly code, the stuff that we just saw on the board a moment ago. And then there's another step that's happening behind the scenes. All of that assembly code is then converted or assembled into object code. So object code is ultimately the zeros and ones. So anytime you've seen in your directories those .o files, some of them you didn't create yourself, right? And odds are you just wondered what they were on first glance. Make clean usually deleted them. Well, what were all of those .o files? Those were object files. Those were the binary files containing zeros and ones that was the result of compiling speller.c or dictionary.c or any number of other .c files that you happen to write. But then there's one last step, and some of you tripped over this early on if you didn't know what flags to use. Sometimes you had to add that -l flag to your make file or -l to the end of your GCC statement. And what did that mean? Or what's an example of having to use -L on the GCC command line? It's kind of a hint up here in a big font, but so linking CS50. So anytime you used getInt or getFloat or getString, you had to link in with -L CS50, and it was kind of stupid, but you always had to put the -L something at the very end of the command line. But that's actually consistent with the reality that this linking step is very much at the end of the whole process. It's sort of the last thing GCC needs to know. So what does that mean? Well, when you compile your code, like let's take an example like Mario.c. So when you have Mario.c and you compile that with GCC, you ultimately get a Mario.o file. But if you also use the getInt function from CS50's library, that means that you had sharp include CS50.h. So the preprocessor copied and pasted all of the .h file's contents, and in there were the function declarations, some global constants, stuff like that. But behind the scenes, what was happening was GCC had to go compile and find CS50.c. And this is a bit of a white lie because we optimized away this particular need. But essentially, at this point in the story, you have Mario.c compiled to Mario.o. You had CS50.c somewhere on the server compiled to CS50.o. So now you have these two independent files, both of which contain a bunch of zeros and ones, object code that Intel CPUs understand. You now need to literally merge these things together, to link them together. So the last step that GCC does for you is it takes this .o file, it takes this .o file, and it smashes them together and lays them out in an appropriate way in memory and on disk so that what you have at the end is just one executable file called Mario or called Mario.exe or whatever the case may be. And then you, the user, can finally run that. So just to put a picture to this, if we have the same example, hello.c. It's a little blurry on the screen here, but here are three of those steps. If I compile hello.c, here is that source code in C at the very top. That's, again, my so-called source code. I compile it. What that gives me then is this stuff called assembly language, which is much closer to the CPU's language. It's much clearer to the CPU what all this is, but it's much less clear, dare say, to the human what all of this is. But it's the same code converted to the basic building blocks, adds, subtracts, moves, that the CPU itself understands. But it's still more English or pseudocode than it is actual zeros and ones. So the final step of assembling is what actually generates, during the assembly process, those zeros and ones. And these zeros and ones are literally what happens when you compile Hello World on an x86, on an Intel computer, using GCC. Eventually, you get those zeros and ones. You actually get a lot more zeros and ones that would fit on the slide, but you get patterns of zeros and ones just like that. So how does the CPU go about executing this program? Well, it essentially gets fed piece by piece by piece. And even though we, the humans, can't really see what's going on here, these patterns of zeros and ones here are laid out in sequences of 8 bits. And you may recall that most CPUs we've talked about in this class are 32 bits long. So our 32-bit architectures, although when we moved to the cloud, it became 64 bits. But for the most part, 32-bit computers are still very much in vogue. So what does this mean? Well, this means a CPU can understand 32 bits at a time. So when you run a program, when you double-click its icon, run it at the command line, 32 bits at a time are fed from your program into the CPU inside of your computer. And some of those bits, usually the first several bits, tell the CPU what instruction to use, whether it's add or subtract or move. And then the last 8 bits and the last 8 bits, after you have 8 or 16 at the beginning, the last bits usually reference these things called registers. So registers, we actually said very early on in the course, are the smallest units of memory that are actually useful to a typical computer. Inside of a CPU are generally 32 or 64 things called registers. And these are very small chunks of memory. It's kind of like RAM, but much smaller. You have 32 bits of memory that is ultimately the location that your operands are stored. What do I mean by that? Well, a CPU, at the end of the day, when it adds two things together, it literally adds this thing to this thing. It doesn't string 10 different values together and add them all at once. It generally operates on 2 inputs at a time. So usually 2 registers are used, 2 little tiny storage areas in memory. The CPU adds those values together, puts the result in another register, and then the process repeats. So in short, it's a huge leap to make mentally from a PHP program or even a C program down to this level of zeros and ones. But there's been many years of development from this low level to punch cards to assembly code to C to PHP, so that everything actually has been built on top of prior work. So if you like sort of what you're sensing is underneath the hood, the course in question here at Harvard at least would be CS141. This is computer hardware. And you can even get a taste of this kind of stuff in like Physics 123, which is a fun hands-on course as well. So there's a lot going on there, but at the end of the day, it reduces to these very basic principles. All right, so here's a more concrete example where we actually have multiple .o files or multiple .c files. So on the left here is just a picture of compiling, again, something like hello.c. But hello.c, remember, uses printf. So that previous pictorial was a bit misleading because we didn't actually acknowledge that there was printf, and in what library is printf defined? And what header file is it declared? Yeah, so standardio.h. So that's because someone else, the people who wrote the C compiler, wrote a file called standardio.c and standardio.h, and inside the .c file is the implementation of printf. So if I'm writing a program called hello.c and I'm using printf, yes, I compile it. That gives me assembly code. Yes, I then assemble it. And again, all of this happens for you with modern compilers like GCC. And out of that comes zeros and ones. Well, there's actually another step here. In this first step, recall that I included standardio.h. So the fact that that gets copied and pasted into my header file is a clue to the compiler that, oh, I actually need the functions that the code that implements printf. Well, where is that? Typically, it's going to be in a file like standardio.c. This lives elsewhere on the system. You don't even have to know or care where it is. But what this inclusion, sharp include, tells the compiler essentially is, oh, you're going to need to use this code. So let me find standardio.c, let me compile it, or make sure it's already compiled. That gives me assembly code. Then I need to assemble that, which gives me the zeros and ones. And then that final step, linking, is to actually merge my bits with the standard bits, merge them together, and get one executable, the hello binary, or hello.exe. So why, though, have you never had to do -l stdio? Since it seems that that was the necessary magic to make this work for CS50's library. Why do you not need to type -l standard.io? It feels like there's an inconsistency here. Yeah, it's common enough that the compiler already links it in. So what does that mean? Well, they're standard for a reason. The fact that it's standard IO, standard lib, means that these are standard enough that you just don't have to provide that linker flag. It's essentially provided for you automatically. So that's all that's really been happening underneath the hood there, is this whole process, but largely unbeknownst to you. And just as an aside, there's one detail that's kind of interesting to realize, especially if you're a PC user. Those of you with PCs, have you ever seen or heard of DLL files? Anyone kind of, sort of? OK. So what are they, if you've all seen them? OK, good. Perfect pedagogical answer. What are they? So what is a DLL file? So that stands for Dynamic Link Library. And without going into too much Win32 or Windows detail, that's the same idea as what's going on here. There's two ways to link programs together. You can either statically link them or you can dynamically link them. Well, what does that mean? This picture here is describing static linking. And in fact, it's kind of a white lie depiction of what you guys have been doing, because generally, if you want this picture to happen, you have to pass GCC the -static flag and say statically compile this. But that's OK here, because the takeaway is that this means static compiling, which means when you get this executable file, your Mario program, your hello program, in theory, you can move that program from computer to computer to computer. And so long as you move it to another computer that has the same CPU, you can run it at the command line or double click it there, and it will simply work. By contrast, if you dynamically link a program, it's not necessarily going to work if you move it to another computer. Any of you who have ever tried to copy programs you've installed on your computer, Microsoft Word or Photoshop or AOL Instant Messenger, it's generally not sufficient to click and drag the .exe file and put it on your other computer or put it on your friend's computer, because there's usually a lot more files that comprise that actual program, many of them these .dll files. So the other way to link programs together is not to create one binary that is the result of combining bits from the left with bits from the right, but rather you just take your own bits from the left and you include inside of the binary, inside of the executable, essentially the path to files on the local hard drive that contain standard I/O bits or the CS50 libraries bits. In other words, it's dynamic in that you need to, in order to run this program, you need to have those other files installed on the computer. So this is good and bad. What is an upside based on that definition of statically linking your programs? What's one good thing about it that comes to mind? Yes?
It takes up less space because you don't have repetition of standard I/O in every.
If you statically link. That's dynamic. OK, so an advantage of dynamic linking is that you don't have this redundancy, right? Because if you're dynamically linking, you just have one copy of standard IO.O or CS50.O, and you dynamically link against them so that you don't make copies of all of the bits comprising those libraries again and again and again. All right, so that's one advantage. And in fact, that's why Microsoft does it with so many of their products, because you can have these shared libraries, these dynamic link libraries, and just not waste disk space unnecessarily. So what's now an upside of statically linking your programs together? Anyone at all? OK?
You don't have the problem that I always get if you're missing a Dll file and nothing will.
Good. So you don't have the problem of double-clicking that program or running it at the command line and being told cannot run, cannot find foo.dll or some other program like that. It's actually self-contained program, a program that's completely portable. You can copy it, move it anywhere, and it simply works anywhere else. So now so we bring this up for two reasons. So one, most everything you've learned in this course, you can certainly apply to Windows programming. So Microsoft and its compilers generally add a bunch of new syntax and conventions that you don't see necessarily in the Linux world. For instance, there's different ways of writing a main function when you code on a Windows platform, and that's just because it's a Microsoft convention. But all of the basics are still actually there. And Mac OS is much more similar, say, to Linux, which is what you guys have been dabbling in thus far. But what tends to happen, especially at final project time, or when you're just out in the real world or just trying to do something for fun on your computer, you'll run into these kinds of stupid headaches. Like, why can't I run this program someone sent me? Well, if they dynamically linked it, it means they didn't send you all of the files that are prerequisite. If you're actually writing a program that you want other people to be able to use, you might need to statically link things, albeit at the expense of making things much bigger than it needs to be. All right, so if we now have programs that are being compiled down to zeros and ones, we have these things called CPUs, which are the brains of your computer, which know how to understand those zeros and ones. How do we actually start storing these things in the real world? Up until now, we've completely taken for granted that we have hard drives or solid-state drives or flash drives or floppies or CDs. There's just some means of encoding data on computers. So how is that done? If you have a hard drive, the mechanical type, which is in most of your laptops still these days, how is data stored inside that thing? Anyone know? What's inside of a hard drive? What's that? Plates. OK, so these metal plates, otherwise called platters, they're these little circular things. And in fact, if you put your ear to a desktop computer or a laptop, you'll often hear something spinning, and that is these platters. So most of you might know at least what a record is or a phonograph player, right? It's actually very similar idea. You have data encoded in circles on that disk, and the thing spins so that the computer can read in those bits from start to finish. So I think a little picture, or better yet, a little video, can do this more justice than my own words. So let me go ahead and open up this little demo here for hard drives. And let's see if this doesn't elucidate.
The hard drive is where your PC stores most of its permanent data. To do that, the data travels from RAM along with software signals that tell the hard drive how to store that data. The hard drive circuits translate those signals into voltage fluctuations. These, in turn, control the hard drive's moving parts, some of the few moving parts left in the modern computer. Some of the signals control a motor, which spins metal-coated platters. Your data is actually stored on these platters. Other signals move the read-write heads to read or write data on the platters. This machinery is so precise that a human hair couldn't even pass between the heads and spinning platters. Yet, it all works at terrific speeds.
In fact, when it says terrific speeds, how fast does a typical hard drive spin? If you've ever noticed on your own computer or at Best Buy when buying one? So 5,400 RPM, so rotations per minute, or 7,200 RPM, or if you buy really expensive disks, 10,000 RPMs. That means it's spinning several thousand times per minute, and on each revolution can some data actually be read off. And the reason for the multiple platters there is, as you may have guessed, just for efficiency. Like, why just have one platter if you can have 4? That means you can store 4 times as much data on there. Well, let's go into slightly more technical detail, still quite accessible, with this follow-up version.
Let's look at what we just saw in slow motion. When a brief pulse of electricity is sent to the read-write head, it flips on a tiny electromagnet for a fraction of a second. The magnet creates a field, which changes the polarity of a tiny, tiny portion of the metal particles which coat each platter's surface. A patterned series of these tiny charged-up areas on the disk represents a single bit of data in the binary number system used by computers. Now, if the current is sent one way through the read-write head, the area is polarized in one direction. If the current is sent in the opposite direction, the polarization is reversed. How do you get data off the hard disk? Just reverse the process. So it's the particles on the disk that get the current in the read-write head moving. Put together millions of these magnetized segments and you've got a file. Now, the pieces of a single file may be scattered all over a drive's platters, kind of like the mess of papers on your desk. So a special extra file keeps track of where everything is. Don't you wish you had something like that?
Sorry, they like to add that. So, but one of the things I've actually always thought is really neat about computer science or about engineering is that unlike some of the physical sciences like biology and such, like we, humanity, actually understand everything that goes on inside of this computer. And frankly, even though I, would not know how to go about making a hard drive, like what metal to use, how to wire all this together, like that's certainly not my forte. What's kind of neat, I think, is that at the end of the day, I mean, all of the comprehension of how this stuff works in your pocket and on your desk is all quite accessible, right? Even if some of that was over your head, hopefully you realize, oh, well, if I just have some way of laying out particles, magnetic particles like this, let's call that a 1. If it's instead like this, let's call that a 0. Well, as soon as you have means of encoding 2 pieces of information, we've seen from week 1 and 2 how you can actually start to represent numbers, how you can start to represent letters, and then ultimately actual computer programs. So let's go ahead and take a look at this one. Oh, all right. So I always offer this too, just so if that was a little so much like this, we also have something for those who still worry that they're among those less comfortable. Oh, damn, won't work. All right, little fail there. Never mind. It's going to be a. I won't tell you. I'll tell you. It was going. No, I won't tell you. Okay. We'll leave it at that. Okay, well, how about this? So this one's just for fun. I'm not going to try to justify this with any academic spin. It's just kind of interesting, I think, because CDs work in a very similar way, but clearly all of us have the means of burning CDs or DVDs. And sometimes you can do this multiple times if it's CD-RWs or DVD-RWs. So this one's, again, just to help you understand what you've been doing when you actually burn a disk for music or data.
How can a CD-ROM disk hold so much more than a conventional disk? The CD drive reads data with a beam of light so narrow that the information can be squeezed together much tighter. You see, a laser diode creates this concentrated beam of light. The light travels through a prism. Then, through a lens and magnetic coil that focus the beam even more. On the underside of the compact disc itself are millions of tiny bumps called pits. That's right, the bumps are called pits. The same surface has smooth areas called lands. These pits and lands are translated into the binary language of bits and bytes used by the computer.
And part 2 of that same sequence is this.
Patterns of pits and lands are laid out along a continuous spiral. As the disk turns, a precise motor keeps the laser beam in place on the pad. Where the laser beam hits a pit, the light is scattered. But where it hits a land, the beam is reflected straight back along its original path. The light enters the prism again, but this time it is reflected at a 90-degree angle and strikes a device called a diode. The diode creates an electric pulse each time the light hits it. So when the laser hits a pit, no light bounces back. When it strikes a land, the diode sees the reflection and sends a pulse. These blanks and pulses are sent to the computer, which interprets them as a pattern of zeros and ones. In other words, into binary code.
So that's how real CDs are actually made when you buy them from the store with a game on it, or you buy it from a music store with music on it. When you actually burn discs yourself, what those things really are, they're really dirt cheap. They're just pieces of plastic. And you can see this if you just run your fingernails or something over it and start do this on something you didn't buy. You scrape the label off of it. Generally, there's just plastic. There's a label for marketing purposes, and then there's some kind of dye on the other side. And that dye, which usually looks green or gold or purple, what happens is when you do burn a CD, some laser light inside of your computer essentially just distorts portions of that dye here and there, so that the next time a laser light actually shines on that CD, if it bounces right back, that means it's a 0 or a 1, whichever. But if it actually hits the part where you distorted the dye and kind of veers off somewhere else, well, that's representing the opposite, the 1 or the 0. So it's still, again, fairly rudimentary. Again, not sure how I even myself would start to build something like this, but the comprehension's probably quite accessible. In fact, one of your classmates on the surveys said a comment along the lines of, when I come into lecture, I always exit realizing how much I don't actually know. And I think they actually said this somewhat out of frustration or just being a bit overwhelmed, which is totally fine and understandable. But, I mean, frankly, that's kind of what makes stuff like this, I think, a little exciting. I mean, we could go off in so many different directions at this point in the semester. We're not going to. But even today, it's meant to just give you a teaser that once you start to understand what's underneath the hood, just a lot more stuff starts to make sense. Google is going to be your friend, and Wikipedia is going to be your friend. And even those of you who don't consider yourself engineers and are going to go through OCS and get consulting jobs or iBanking or whatever, what's really kind of cool about having some technical know-how, whether you are or not a computer science major, is that you can start to tell much more effectively when people are BSing in the real world. Right? There's a lot of people who kind of talk about technology and this and that, and hopefully, and after a couple of more weeks of this class, you'll start to be able to see who's quite just talking and not really understanding what it is they're saying. You'd be surprised how often this happens. Frankly, go into Best Buy or a technology store, and already, even just after seeing videos like that, might you understand what's being sold a bit better than the person selling it to you sometimes. All right, so you have one of these things called floppy disks in your hand. Might not have used or seen these things in some time. They do actually still sell them. They only store how much data? Yeah, 1.44 megabytes, so 1 million bytes, or 8 million bits. Well, let's take a look at what's inside, and you'll find it quite similar to what's inside of a hard drive, but much cheaper and much slower.
The floppy drive you see here works with 3.5-inch floppy disks. They're the type most often used to carry new programs, save data, or to move files from one PC to another. The part of the disk we see is actually just the hard plastic shell. The working disk, which is inside, is protected by a sliding metal shutter. This thin inner disk, called the cookie, is coated not with chocolate chips, but with a very thin layer of magnetic material. When you slip the disk into your floppy drive, a system of levers pushes back the metal shutter. The levers also pinch two read-write heads closer so they almost touch the cookie. A motor at the base of the drive spins the cookie based on commands from your PC. The PC also signals another motor to move the read-write heads back and forth over the surface of the disk so they can read or write data. Before your PC writes data, your drive first checks the Write Protect tab in the corner of the floppy disk. If it is open, light from a tiny diode shines through and strikes a diode on the other side. This diode then says to your PC, "Don't write on this disk." But if the tab is closed, no light gets through, and the PC knows it's okay to write data.
So be careful, because there is, in fact, little bits on this thing, but you can probably see, as the clicking suggests, that you just move this cheap little metal shutter, and inside of there is, in fact, this cookie. In fact, it's all right if you ruin a few bits. Go ahead and just push down on that. And the reason these things are called floppy is not because they're actually pretty hard, because they're in this plastic shell, but because that thing inside of there is, in fact, itself very floppy. Let's see if we can't dive a little deeper. But again, to this point of things being sort of simpler underneath the hood than you might think, it's such a stupid thing. Well, let's make a hole in the piece of plastic, and if light shines through it, it's locked. If light doesn't shine through it, it's not locked. So again, very basic things under here. Let's look at this final clip here.
To write data onto a floppy disk, your PC tells the drive to send tiny pulses of electricity through the heads. The pulses make the heads act like little electromagnets. Each head creates a magnetic field that reaches the surface of the disk. Remember the magnetic coating on the cookie? The magnetic field alters the tiny particles in this coating. If current runs through the heads one way, the particles are arranged with their north and south poles in one direction. But if current flows through the heads the opposite way, the polarity reverses. To read data from the disk, the read-write heads move into the same position over the cookie, but this time the process is reversed. The cookie particles create a magnetic field in the coils of wire, and this creates a current in the read-write heads. The disk drive detects this flow of electricity and passes it onto the PC. The PC translates the back and forth current changes into a series of ones and zeros, the binary language of computer data.
So we're well aware that many of you would really like to just break something when you're working on CS50. So we thought we'd give you that opportunity here toward the end of the semester. Beware the little spring that's likely to hit your seatmates in the eye, but go ahead and just remove this plastic or this metal shutter, and you'll actually now expose the inner cookie, and this is the most gratifying part of all. Insert your fingers at the bottom of the plastic, and voila, a little souvenir. And the entire magic that made for years software distribution possible and the storage of millions of bits, this little thing in there. So whether you were among those less comfortable somewhere in between or more comfortable, a lot of the stuff we've been talking about really boils down to some fairly basics. Why don't we embrace the fun that you've just had? Actually, it doesn't sound like you're having much fun, but consider this your souvenir. Please take it with you when you go. That's it for today. No Class Wednesday. We will see you on Monday.